9-4 that I'm skipping, if you get a chance to get bored or you want to look at it, it's over sequences, which is really just patterns, right? And there's two types of sequences. There's arithmetic sequences, which means like when you add to get the next number in the pattern. There's geometric sequences where you multiply to get the next number. And then 9-4, there's all these formulas of how you can write an equation for a sequence or pattern, and what you can do when you add them up. 9-5 is when you add up a sequence. Like, what is the sum if I add up the first 10 terms of this? Again, we're kind of skipping over that part in the whole scheme of the math world. Are writing equations for sequences, you know, in the top 100 things you should know? Probably not. But it's something that I usually do. But something that I think you should know is how we can use the notation here. The summation notation. And so I made you, look, you already see it. Here's your thing you have to write. This is a Greek letter. You know this Greek letter? Sigma. Someday you're going to go to college, and there's a good chance you're going to join a sorority or a fraternity, and maybe Sigma will be in there, and then you're like, oh, I remember precalculus. Or you'll at least see the buildings with the big letters on it. Or when I was in college, all the sorority girls had bags with their Greek letters sewn on them, embroidered on them, and Sigma is a very popular one. But that is a Greek letter, and in math, it doesn't mean sigma, it doesn't mean fraternity or sorority, it means summation. So when you see sigma, you know it means the sum of something. And so I said it's the sum of a sub k from k equals 1 to n. So notice the k here, whatever letter is here, will be right here. Sometimes it's K, sometimes it's I, sometimes it's J. Usually one of those letters, but it really could be anything. And it tells you where to start, right? So K equals 1 is your lower limit, or that's where you start. And the number on top tells you when to stop. So the upper limit is where you stop. And then this part, a sub k, is what you're trying to add up. It's going to be some formula, and I'm going to show you in this example. It's probably going to be the easiest way to do that. So my example So notice on this one, they use I instead of K, but still whatever this letter is this letter. And they're telling me that we're going to go from 1 to 5, which means I'm going to plug in I equals 1. Then I'm going to keep going. I'm going to plug in I equals 2, I equals 3, I equals 4, I equals 5, and I'm going to stop at 5 because that's my upper limit. And then I'm going to add them together because that's what sigma means. It means the sum of those terms. So if I plug 1 in here, I'm going to show a lot of work on this one. I'm going to say that 3 times 1 plus, if I plug 2 in there, that'd be 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. I started at 1, I ended at 5. And the summation, the sigma, just means I add those up. So I get 3 plus 6 plus 9 plus 12 plus 15. You can see that's a pattern there, right? That's what we skipped in 9-4. That would be the pattern, 3, 6, 9, 12, 15. Does that add up to 45? So it never says the word add those up, but that's what you need to know from that notation. You need to know sigma means your answer is the sum of those terms. Questions about that? Okay, so then I made it a little more complicated on number 2 there. Number 2, again, usually this is 1 down here, but it doesn't have to be. So pay attention to what that number is. Sometimes it might start at 0. Sometimes it might start at 10, right? So like pay attention to what it is. And then we're going to stop at 4. And notice in this one there are 2 k's. So you just replace k for each one. right? So that would be like negative 1 to the first power times 1. Plus, I'm going to do that for 2 and 3 and 4, and I'm going to work it out. And definitely you can use your calculator. Definitely you don't have to show as much work if you don't want to, but I just want to show you where those numbers are coming from, the 1 through 4, and I'm just plugging it into that formula. So on this one I would get negative 2. But on this one, the negative 1 squared means it's going to be a positive. 2 times 2 is 4. And then the next one's going to be minus again. That negative 1 is going to mean we're going to alternate signs. That's going to be minus 6. And then negative 1 to the 4th should be a positive 8. 4? Is 4 the right answer? There's actually a really cool thing that you can talk about an infinite series. We're not going to do that right now. Maybe we'll do it after break. But instead of adding up like 1 to 4, you can add up 1 to infinity. And you can actually add an infinite amount of something, which kind of seems like an impossible thing to do. But there's a really cool thing. So maybe after break we can talk about that. But for now, I just need you to be able to know what this is, because it kind of leads us into 9-6, which talks about adding up integers and formulas that work for you. So the next slide here, section 6 is called mathematical induction, which is actually a way to prove stuff, and we're going to talk about that in a minute. But before that, there's a formula that you can do if you want to add up consecutive integers. So if I just wanted to add up 1, 2, 3, 4 all the way to n, there's a formula for that. And it is, if you take n times n plus 1, and you divide by 2, you can add up consecutive integers. So if I said add up 1 to 100, you could take 100 times 100 plus 1 and divide by 2, and it'll give you the sum of those integers. And if you notice, I just have formulas where you did these, and I'm not going to lie, some of these get a little crazy. But you can add up the sum of consecutive square integers to the 4th and to the 5th. Alright, and they all just have to do with what number you end on. Could you type all that in your calculator? You could. But if I asked you to add up from 1 to 75 cubed, that's going to waste a lot of time typing all that in, whereas if you have this formula, it's going to be a lot quicker. So if you add up the square integers, it's n times n plus 1 times 2n plus 1, all divided by 6. The cube one isn't so bad. It's n squared times n plus 1 squared, all by 4. And then the last ones kind of just get a little out of control. So the 4th power, we're going to take n times n plus 1 times 2n plus 1 times 3n squared plus 3n minus 1. All over. And the last one is n squared times n plus 1 squared times 2n squared plus 2n minus 1 all over. And I will tell you, I wasn't going to tell you yet, but just because this kind of usually leads to that question, do I have to memorize all these? I don't have it memorized. As you can see, I was looking at the paper. For this test, and we'll talk about it more later in the week, but for this test, I'm going to let you make a sheet of formulas. You are restricted to formulas, so you can't write examples and notes and all of that. But like this, you can put on your formula sheet, so you don't have to feel like overwhelmed that you have to memorize all this, because you don't have to memorize it as long as you make the formula sheet with the formula. What I want you to be able to do is, if you have it, to know how to use it. And so I think I put a couple examples on here. I could just ask you to add up something, but I could make it a little more. So I could just ask you to add up in cubes, which you could just do. Let's do this in cubes, let's 4 cubes. But I thought I would do a little more complicated stuff. Could you, again, on the test, could you do this by hand without using those formulas? Definitely. If I added that to be 100 instead of a 10, maybe not so much could you do that by hand and have the right kind of things. But I want to show you how you can use these formulas to help you. So this kind of leads us to that summation notation. You can separate things in a summation. So it's 3, right? You can write that as 3, and then you can put the summation between it, so you can kind of separate the 3 times that. You can multiply everything by 3 again. Let's say n equals 1 to 10, and then I can write that as n cubed. It's also a property of summations that you can break up addition and subtraction. So I can separate that, so I can take minus 2, right? Because if it's 2 times n squared, I can just take 2 times all to n times the summation from n equals 1 to 10 of n squared. And if you can break it up as n squared, n cubed, into the 4th, or into the 5th, I can now use those formulas. So instead of doing 1 cubed plus 2 cubes plus 3 cubes plus 4 cubes plus 5 cubes, you can do that. Or you can use the formula I just gave you. I told you that the sum of adding up n cubed was n squared times n plus 1 squared over 4. And again, 10 isn't that bad. 100 would be bad. So I could just use n is that top number, right? N is 10. So I could just take 3 times 10 squared times 10 plus 1 squared. I'm going to go ahead and say it. That's 11 squared. All over 4. And even if it's not that much work to add up to 10, definitely less time using your calculator, less chance for error if you use that formula. They have it. And then I could do the same thing for n squared. So I have this minus 2. And now instead of doing 1 squared plus 2 squared plus 3 squared plus 4 squared on and on to 10 squared, I'm going to use that formula that I just gave you for n squared was n times n plus 1 times 2n plus 1 all over 6. And again, this one, n is 10. So that would be 10. N plus 1 is 11. 2 times 10 is 20 plus 1 is 21 all over 6. Be careful typing things in your calculator. We're adding up integers, which means I don't think we should get a fraction here. $770 on that one? Did anyone else get that? So this is in 9-6 stuff. They ask you to add up some stuff. Sometimes they write it out as like 1 squared plus 2 squared plus 3 squared. Sometimes they write it as summation notation, which is why I wanted to make sure I hit on that from 9-5. The only other thing that I want you to know about from this chapter is, how do we know that's true, right? I gave you those formulas and you just accept them. I was like, yep, they must be true. She told me they're true. But how do we know they're true, right? Someone a long time ago said this is the formula. But everything in math, there's a proof to go with it. And so, how do we know those formulas like that are true, or any formula that says that this pattern continues, this is what it adds up to? We have to do a proof for that. And in geometry, you learn lots of proofs. You learn 2-column proofs, and paragraph proofs, and flow proofs, and indirect proofs. And today I'm going to show you another kind of proof, which is called proof by induction. The good news is, I'm not going to make you prove some of those crazy ones. We're going to start a little bit easier. But just know all of those are provable. This is how your book talks about math induction, and so I want to make sure I kind of use the same language. But basically, the good thing about math induction, it's a 2-step proof. Alright? So it's not like the 2-column proofs where you have to kind of figure out what to do. And it's very algebraic, so if you can just kind of follow the process, it works itself out every time. And they're never going to give you a proof that's not true, which means it has to be true every time. Which means the in-between steps are important actually to follow it. So it says, let P sub n be a statement involving some positive integer n. Step 1, show that the formula works for 1. So step 1, P1 is true. Show it works for n. That's the easy part. It's like the given in this 2-column proof, right? You know to do that part. Step 2 is a little bit more abstract, but it says the truth of P sub k, where k is some value in between 1 and n, implies the truth of P sub k plus 1. And if that's true, then P sub n must be true for all positive integers. We're going to work through one in a minute, so I can kind of work you through what that all means. But I do want to show you that there's one on your homework that's not a proof. It's just practice to go from, how do you go from P sub k to P sub k plus 1? So there's one on your homework, and I'll make sure I'll tell you which number it is, because people always just try to do the proof for it. It doesn't say prove this, it just says show, if this is P sub k, what would P sub k plus 1 be? It just means the next term. Right, so if this is P sub k, P sub k plus 1 is the next one after it. So everywhere I see a k, guess what I'm going to replace it with? K plus 1. It's really not that crazy. So k squared becomes k plus 1 squared. K plus 1 squared is going to become, I'm going to replace k with k plus 1, but then I still have that plus 1 there, right? So that's really going to become k plus 2 squared, and the bottom doesn't change. So the k plus 1 term is just changing every k to k plus 1. Questions about that? How I look up two examples on here. So let's kind of work through one together, and then we'll kind of hopefully have time to right? And it's really, if you can get past the word proof that makes you all want to run in the other direction, if you can get past that, it's really step by step, as opposed to sometimes proofs in geometry, you kind of don't know where to go. You know where to go every time if you can just follow the So, it says, use math induction to prove this is true. So let's kind of look at what we're proving. It says, if I continue this pattern, 3 plus 7 plus 11 plus 15, every time what's happening? I'm adding 4, right? So the next one will be plus 19. If I continue that pattern, it says, the nth term in that would be 4n minus 1. So think about 1, 2, 3, 4. If you plug 4 in there, 4 times 4 is 16, minus 1 is 15, right? That works. That's the pattern. It says says if you want to find the sum of all of that, it will add up to n times 2n plus 1. All right, those are the kind of things we want to prove, kind of like those formulas on the first page. How did we know those were true? Proof by induction can show that. So step 1, we're going to prove it's true for p sub 1, which means all we have to do is plug in n equals 1 into these formulas and show me that I get a true statement. Again, it's like the given in your two-column proof. So when n equals 1, I'm going to get 4 times 1 minus 1 equals 1 times 2 times 1 plus 1. Well, minus 1 is 3. 2 times 1 plus 1 is 3 times 1 is 3. Okay. I don't know that you have to check it. I like to check it. Step 2. We have to prove that if p sub k is true, then when we do p sub k plus 1, it's also true. This is where you have to think about a proof is showing how you get the final answer. I know what the final answer is going to be. It's going to work, but I need to show the steps in between. So this is where it's really important that you actually write out all the steps. Step 1, maybe it seems like a not important step, but we have to say, well, where's p sub k? We don't have that. So let's assume that p sub k is true. Why do you pick k? I don't know. You gotta pick something besides n. N is like the last number. 1 is the first number. So the k number is just some number in between 1 and 2. Alright? If you want to pick something other than k, you could. But k is 0. So if I wanted to change this, maybe we should do this. Say this right now is p sub k. If this is p sub n, what do you think I would do to get p sub k? Everywhere there's an n, you just replace it with an n. That's it. So for p sub k, all I'm going to do is rewrite that whole thing, but replace n with k. 3 plus 7 plus 11 plus 15 plus dot 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 plus 4k minus 1 equals k times 2k plus. We're saying that's true, right? 1 is true, so some number bigger than 1 is also true. If you remember indirect proofs from geometry, you assume the opposite's true. So like the word assume kind of comes up a lot in proofs. What we want to do is prove that p sub k plus 1 is true. So there's 2 parts to this, and you can tell me how you want to do it. I've always done it in 2 separate parts because I feel like I write too big, but in the past we've kind of been able to squish it in on one line, which maybe makes more sense. But we have to come up with the p sub k plus 1 term for this side and this side, right? Like both sides of the equal sign, and show they equal each other. Okay, so my next step is I want to figure out, I want to say, what does p sub k plus 1 equal? On this side, do you agree that this whole thing is p sub k, that I would have to write the k plus 1 term would be 3 plus 7 plus 11 plus 15 plus this plus the next term? Because I'm writing out all the steps. Like if I said the first term, if p sub 1 equals 3 and p sub 2 equals 7 and p sub 2 equals 3 plus 7 and p sub 3 equals 3 plus 7 plus 11. For every term I write, I have to write the ones that were before it with it. Does that make sense of what I'm saying? So for the k plus 1 term, I'm going to write all this again. I'm going to write 3 plus 7 plus 11 plus 15 plus dot 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 plus 4k minus 1 plus, I have to write the next term, the k plus 1 term. So, like, for number 2, I wrote number 1 plus the second term. For the third term, I write 1 plus 2 plus the third term. So for the k plus 1 term, I'm going to write all the terms before it, plus how would I write the next term? If 4k minus 1 is the k term, how would I write the k plus 1 term? Just like we did in the last problem, I'm going to replace k. I'm going to write 4 times k plus 1 minus. So I write all that before there, plus the next term. That's my k plus 1 term on that side. I want that to equal the k plus 1 sum. So again, kind of a good way to think about it is I have to replace all the k's with k plus 1. So on this side, this is what it adds up to. The k plus 1 term is going to be k plus 1 times 2k times, just kidding. 2 times k plus 1 plus 1. So everywhere there was a k here, I've replaced it with k plus 1. Because that's what it adds up to. That's the sum. This is the list of the terms. If you fit that all in one line, I used to always do this in separate parts of your line, but people got really confused by this, so I'm trying to, because this makes it not confusing. It's our first one. Anyway. Okay, so this part's the sum of what it adds up to. So what it adds up to, you replace every k with k plus 1. But this side is just a list of all the terms, right? So I erased my thing here. But this is like if I said P1 is 3, P2 is 3 plus 7, P3 is 3 plus 7 plus 11. Like when I ask for the third term, you don't just say 11, the third sum, you have to list them all. So when I ask you to list them all on this side, because it's adding 3 plus 7 plus 11, you have to include the one before it. Does that make sense? And the nice thing is, all that changes in these proofs is the problem, but every time it's something adding up equals some sum, and every time you're going to include the one before it and then do the very next one. And so once you do a few of them, you kind of just get happy with them. But that's why, because you have to add the one before it before you can add the next one. Okay, this side is the easier side to work with. So we're going to work with this, and then we'll go back to this side. Could you just simplify this? Just multiply. It's much harder to add up something like this. But over here, I could just work out k plus 1. That would be 2k plus 2 plus 1. So is that just 2k plus 3? And then, I don't know, do you want to just work it out? 2k squared plus 3k plus 2k would be plus 5k plus 3. What I'm trying to prove is that when I add this up, which I don't know what k is, some arbitrary value, then it's going to equal this same thing. So, how do I add this up? Do I know what 3 plus 7 plus 11 plus 15 plus ... plus 4k minus 1 adds up to? Do I know what 3 plus 7 plus 11 plus 15 plus ... plus 4k minus 1 adds up to? Every time. That's why it's so important that you put the p sub k. That's why you say, assume this is true. Because we know all this adds up to this. Which means you can replace all of this with this value. So I'm going to draw a line there so you can see in your notes where's that coming from. Right here, you draw a line. That's going right there. You don't have to draw the line every time. You can if you want. But I just want you to see where that's coming from. And so I can replace that. I'm going to say p sub k plus 1 equals, instead of all that, I'm going to say what I know it adds up to. It adds up to k times 2k plus 1. That only takes care of the p sub k part, right? Because that's just p sub k. And then I'm going to add that extra term, right? So the extra term that we didn't add up yet is the 4 times k plus 1. Which means, now that we know that adds up to just p sub k, can I simplify this side? And what should happen is that should equal this. So the good thing is you know where you're supposed to end, and if you don't end that way, then you just have made some multiplication mistake, regression mistake. P sub k plus 1 equals 2k squared plus k plus 4k plus 4 minus 1. We could just say should equal 2k squared plus 5k plus 3. I just want to end with those equal the same thing. And this is the part that I get really happy at because I can see they equal the same thing. So p sub k plus 1 equals 2k squared plus 5k plus 3. That was the pattern part, the plus plus plus. And it equals 2k squared plus 5k plus 3. Or like the real thing you're supposed to do. Like this, I think that. Or upside down. Or you could do this. Those are real math things. This is some Latin word that means like you proved it. I like check marks. You don't have to do it. But they equal the same thing. This seems kind of crazy, and mostly it seems crazy because it's new and it seems a little, like how am I supposed to do this on my own? But how else do you prove when you add something up that goes on forever that it equals something? I got an email once from another math teacher talking about like how they explain it outside of math terms, and I don't know that this will make you any happier, but I think it's, but it says, relating proof by induction to climbing a ladder. So it says, if I want to prove that I can climb a ladder with infinite rungs, I must do the following. Yes, I know you would die before you climb the ladder with infinite rungs, but just assume that you live forever as well, okay? Step 1, I'm going to show you I can get on the ladder. That's the first step, right? We prove it's true for 1, so I'm going to prove to you I can get on 1 rung. Second, I'm going to show that if I'm on any rung on that ladder, that's the k term, then I can get to the next term, or the next rung, which would be k plus 1. So that's where the whole k and the k plus 1 kind of comes in. And then that proves that I can climb forever, right? Like, I'm sure you could argue with me about this, but I thought it was kind of at least something to visualize of where this k and this k plus 1 is coming from in terms of climbing a ladder. So I think we should do it. It would be much faster now that we know what we're doing. You will have a proof by induction on your test. It looks gross, but it's really not that bad. Notice on the last one we were adding, what are we doing on this one? We're multiplying. Well, we're adding in here, but we're multiplying the terms. So this is like the first term. This is the second term, right? So we're multiplying. That's the 2 types of sequences that we skipped over in 9-4. When I write my proof, here's what I'm going to say. Step 1, prove n equals 1 is true. So I'm going to plug in, this is my first term, so I'm going to say 1 plus 1 over 1 equals the sum when I plug 1 in. 1 plus 1. 2 equals 2. Hooray! Halfway there. We're going 2 steps, right? So we're halfway there. Step 2. Every time, assume p P sub k is true. And yes, you need to write that. And I know that people think it's silly, but it's important. If you don't assume that P sub k is true, then you can't prove k plus 1. And every time, I'm going to write my P sub k term. And just like the last one, what's the only thing I have to do into this original problem to change it to P sub k? Change my n's to k's. And you can even be extra lazy if you want. And not write all 3 terms, right? Oh my gosh, that's so much to write. So you can just write the first 2 terms, and then you can say dot dot dot. 1 plus 1 over k equals k plus 1. Those things are the same things you do in every proof. Prove it's true for 1, assume P sub k is true, change your n's to k. And then you have to do your k plus 1 term. So now, this is the big thing I'm trying to prove. We want to prove P sub k plus 1 is true. I just write this. And this is where you can do it separately, or we can try to squish it all in, which I think is going to work. I'm going to add up this whole other term, not add, multiply this time. 1 plus 1 over 1 times 1 plus 1 over 2, dot, dot, dot. 1 plus 1 over k. Right, so I'm doing the k one, but no addition sign this time. Multiply by the next term. Right, so don't forget that one. And then the next term would be 1 plus 1 over k plus. That's probably the one mistake that people make a lot, is they want to skip that. But remember, you need the whole P sub k there, and then you do the k plus 1. But on the other side, to change this to k plus 1, I just change the k to k plus 1 plus 1, because that's the term. And again, what's my goal here? My goal is to make this side equal this side. This side's the easy side again. That's just k plus 2. Okay. This side's not so bad now, because we know every time. We know what 1 plus 1 over 1 plus 1, or times 1 plus 1 over 2, dot, 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 times 1 plus 1 over k. We know that's just P sub k. So every time, I can say that's just P sub k times the next term, which is 1 plus 1 over k plus 1. Okay, so P sub k times that. And I know it's supposed to equal k plus 2. And where do I get what I plug in there? What do I plug in? Yep, sub k. Right here. So now we write that step out. We know P sub k adds up to that. So I can replace this with k plus 1 times 1 plus 1 over k plus 1 equals k plus 2. Well, dang it. Those don't look like they equal each other. And they're fractions, which means I better just stop, right? I think I have to go to common. Right? Adding this together. If I get a common denominator here, you agree that this just becomes k plus 1 over k plus 1. Plus 1 over k plus 1. Right? Because I can't add these together. 1 with 1, so that makes a constant here. One times the rate. I just gotta come down here, right? If you have this thing. Here's the thing, like all that algebra you've been learning your whole life, that you're like, why do I have to use this? It's here, right? This is why. So if I add this, how do we add fractions? We keep the bottom the same, and we add the top. So k plus 1 is just k plus 2. Then when I multiply, can I cross out those k plus 1s? Oh my goodness. K plus 2 Every single proof is the same setup. The algebra is just different. All right? So use this to help you as you do your problems tonight. 1 and 4, those are proofs. Number 10, not a proof. And then I think this is from 962. Oh, that's on your paper. So not your assignment sheet. Do this instead. Okay? Goodbye. Happy proofing. That's just more proofs, not proofs also. These last 5 are doing those formulas. So I think there's only 2 proofs.
Jacob Beatles, Cody Wyatt, Caleb Payne, Alpha Button, and Elizabeth Button. The office, please.